Here we've got a system of combined masses. Two masses, mass M1, which is 5 kilograms, and mass M2, which is 15 kilograms. They're connected by a rope, and we'll call this rope 1. Attached directly to the 15 kilogram mass is an additional rope, rope 2, and it's being pulled to the right with a tension force of 50 newtons. So the whole system, if it's going to move, is going to move to the right. Now there is some friction, and the coefficient of friction between the ground and both boxes is 0.15. Now we're going to look at this three different ways. We're going to look at all the masses together, in other words, the entire system, and then we're going to isolate the individual masses. In all three cases, we're going to do the same thing. Free body diagram, and then an equation of motion, and then solve. And we're going to see what we get when we do that. So let's look at the entire system. We have two masses. Obviously, we've got forces of gravity. I'm going to label mass 1 Fg1, straight down. Mass 2 is bigger, so I need a longer vector, and I get Fg2. Now, these masses are on the ground, and the ground is holding up these masses. So there must be an equal and opposite force called the normal force as a result of the masses squeezing the ground. F normal 2 acts on mass M2, and F normal 1 acts on mass M1. Notice that they're equal and opposite to the vectors Fg1 and Fg2. We know that because these masses are not moving vertically, so all those vertical forces must cancel one another. Now what about horizontally? And these are the forces that matter. These are the forces that are driving the system. Out the front, it's already been stated that I have this pull force, this applied force. I'll label it F applied, and we actually know the value. It's 50 newtons. Now, both masses have friction attached to them, and friction always opposes the motion. So mass M1 will have a friction force pulling it back, and we'll call that force of friction 1. Similarly, mass M2 will have a friction force pulling it back, and I'll call it force of friction 2. Now, the last two forces that we need to concern ourselves with have to do with rope 1. Now, ropes always pull. You can't push a rope. And Newton's third law comes into effect. This rope is attached to two different masses. On mass M1, the rope is pulling it to the right with a tension force. I'll call it Ft. On mass M2, there's a rope pulling it back to the left. Same rope, same tension. I'll call it Ft as well. Notice that both those forces are equal and opposite, and they will cancel when I do my equation of motion. Now, my forces are not drawn to scale. I've just identified all the forces that are present. Next step is to do my equation of motion. Now again, all these green vectors, all the vertical ones, cancel each other off. So the net force in the y is 0. Let's focus on the horizontal forces in the x. So my net force in the x is always the sum of all the forces that are present. It doesn't matter what order we do it in, but anything opposing the motion will be negative. So if I look at force of friction 1, it's going against the motion, so I go negative force of friction 1. Similarly for force of friction 2. My applied force is positive, it's driving the system. I'm just going to directly put 50 newtons in there. And then I've got these two tensions. One is to the right, and one is to the left. So one's positive and one's negative. Now notice when I do the entire system, these tension forces that connect the masses together cancel each other off. So I'm left with a simplified equation. Now F net we know is always ma. Force of friction is always mu times the normal. So my force of friction 1 will be mu times Fn1. My force of friction 2 will be mu times Fn2, and they're both subtracted because they're going against the motion. Plus 50. Now it's just a matter of putting in the values. So I'll continue on to the right. I'll put a comma here. Now what do I put in here for my mass on my F net side? Well, since I use the entire system to come up with my F net equation, this would be my total mass. So 5 kilograms plus 15 kilograms gives me a total mass of 20 kilograms. We don't know what the acceleration is. Equals negative. Now my coefficient is 0.15. my normal force 1, if you look at my original vector diagram, my normal force is equal and opposite to Fg1. So that means my normal force 1 is going to be mg, 5 times 9.8. Just the mass 1's mass is all that matters there, because it's creating that force of gravity 1. Similarly for mass 2, Fn2 will be mg as well, 15 times 9.8. And then all of that we add together with 50. So when you work all this out, work out all the right-hand side and divide it by 20, you should get an acceleration of 1.03 meters per second squared, and that'll be to the right. That's driving the system. So now we know the acceleration. Let's look at what the tension is in rope 1. Now, first of all, notice when I did the entire system, it doesn't help me with the tension, because the tensions cancel when I look at the entire system in the middle. So let's isolate. Let's look at mass M1 by itself. Okay, we know some forces. Fg down, F normal up. Now I only care about forces that are directly attached to M1. There's a force of friction pulling it back, which we've already identified. And then the only thing that's driving it forward is this tension force. So that's it for mass M1. Now again, F normal 1 and Fg1 cancel each other out because it's not moving vertically. So my equation of motion for mass M1 will simply be F net equals Ft, which is positive, minus force of friction, which is opposing. Now once again, F net is always ma, Ft is what we're looking for, and friction is mu times the normal. And in this case, my normal is exactly equal to Fg1. So there's my normal force, m1g. Now what do I put in the mass this time? Well, I only used mass m1 to come up with my equation, so this will be mass 1. Now we're solving for Ft, so if I isolate Ft, I get Ft is m1a plus mu m1g. Putting in the values gives me 5 times 1.03 was my acceleration, plus 0.15 is my coefficient, times 5 times 9.8. And when I work all that out, I end up getting a tension force of 12.5 newtons acting on mass M1. Now, one way to check if you're doing this correctly is to repeat the process on mass 2. You should get the same value for the tension, according to Newton's third law. So let me just change colors here. I'll do it in blue so we don't get it all muddled up. The forces acting on M2 are as follows. Same tension pulling it back, which is what we're looking for. There's some friction pulling it back. Force of friction 2. And in this case, we've got a 50 Newton force and applied force pulling it to the right. Now, once again, we've got these vertical forces which cancel each other out. Fg2 and F normal 2. So Fg2 and F normal 2 cancel each other off vertically. There is no net force in the vertical. Let's focus on the horizontal once again. So I get F net for mass 2 is 50 newtons, which is positive, minus force of friction 2, minus force tension. Both those are opposing the motion. Now F net is always ma, in this case mass 2. Force of friction is mu times the normal, and in this case my normal force will be m2 times g. In other words, Fn2 is Fg2. They're equal and opposite. Minus Ft. Now if we isolate for Ft, I get 50 minus mu m2g minus m2a. And if you work all that out, you get 12.5 newtons as well. So the tensions agree, we should be correct. Now, in terms of significant figures, we'll round off our tension. Instead of 12.5, because we only have 2 sig figs in our question, we'll say our tension is 13 newtons.